Hello and welcome to another edition of Espresso Engineering. Today I'm here with James Ritter from Washington Laboratories, and we're going to discuss the actual properties of capacitors and other filter type components as opposed to their theoretical. James, you've worked in the lab a lot and you've seen a lot of different things on that. What can you tell us?
Well, I tell you, a lot of times I've seen things that really aren't the way they should be. When they put these parts on, I know all the time when people have problems with these boards, they go running for those parts bins.
Yeah, they do.
And they get themselves into serious trouble.
What types of things do they ignore, if you will?
Well, a lot of times they grab things out of these bins and just start soldering them down everywhere. You know, when they get into manufacturing, they don't quite go in that same way.
So then the actual installation of these parts is very critical.
Oh, it has a tremendous effect on what you're trying to do. And if you're using just basic passive parts, then looking at values, tremendous effect. And you can go seriously astray if you don't use good engineering practices.
Now, we did have a product that came back yesterday that didn't seem to be quite fixed right. Was that correct?
That was a perfect example of this. We come and we started tacking caps down. We had 2 or 3 problem frequencies. And we actually thought we had it solved. And, you know, the engineer went away happy. Fortunately, when they came back on the boards, they weren't quite in the same way we put them in. And now, unfortunately, I'm sending them back home.
Oh my, that can be difficult. They probably could have really benefited from that other presentation that you gave a couple of months back on the different components and the lead links and things.
This is typical. I do that a lot. And, you know, just so happens, I did it just the other day, and I still have that set up to look at.
Well, maybe we should take a look at that.
I think that would be a good idea.
Great plan. Let's go.
Well, Steve, here we are.
Oh, that's an interesting looking setup.
Would you mind lending me a hand while we show how to do this?
Absolutely.
All right, well, what I got here is a standard network analyzer. What this does is it measures the transfer characteristics of devices, puts out power through one port, and reads it into another. Typically, a lot of times you'll hear these referred to as scatter parameters. What we'll be looking at today is what's called S21. We'll be putting power into the unit and reading it through it out to the other side. We'll kind of get an idea of what our devices are doing to our signal.
Great.
Right now I've got this set to sweep from about 300 kilohertz up to about 800 megahertz. And we're going to look at some typical situations that we fall into. When you have one of these devices, the first thing you need to do is get your test setup out of the way. So what we have here is a test setup with 2 cables, and we don't want this device measuring any of the characteristics of our test fixture. So these devices incorporate a feature which allows you to put a straight through in, and it will null out and save any characteristics of these cables. That way what you're reading is indeed what you want to read and no additional factors. Piece of combined, we'll put a short in between these.
Oh, this is the short?
That's the short. Just a straight piece of wire running from one end to the other end. We'll calibrate our test fixture. Do this, and most network analyzers have a function called normalize. When you hit the normalize, it will take this reading, store it in there, and you should end up with a straight line on any of your screens. And when you see that, you're ready to go. Now I have this network analyzer set up to read in 10 dB increments. Obviously a short falls right at the 0 reference marker, which means nothing is happening to it. All your power out is flowing straight through and you're receiving all your power in on the other port. One of the problems I see typically in the lab is that a lot of times customers, people with problems, will have 1 or 2 problem frequencies they can't get rid of. And they'll go for passive components. There's all kinds of passive components, but the most common ones that people use are capacitors. And unfortunately, they'll open a bag up or go to a bin, and they'll grab one of these ugly-looking things here. See that I have a capacitor here. Has about 1 inch to 1.5 inches worth of lead on it. What they'll do is they'll start tacking these. If you'd be so kind to put that in, we'll see what kind of effect this has on our transfer characteristics. I don't think that's there. And you know, most capacitors, when you put them in, they have a fixed point which is basically 1 over 2 pi fc, where f is frequency and c is capacitance, and they form in the filter world that's known as a notch. They have a very well-defined point. In this typical scenario, what we have actually is a capacitor that's across the line going to ground. So at that point, it has a low impedance at the bottom point of the notch. And what it'll do is it'll draw any signal down at that frequency to ground. And it will not feed further on down the line. So what does it say? I have a problem around 43 megahertz. If I put the marker from the analyzer, you can see it's about minus 30, 35 down, which means it'll attenuate that signal by that much. And if you're unlucky enough that to be your problem signal, then it'll go away. The reason I'm saying unlucky enough is because a lot of times if you put this on your board in the lab in that configuration, you may end up problems later on. Yet, you hit the right frequency, you got rid of your signal, but when you go back, say I run back as an engineer, I'm real happy, I fixed my board, go make me 100,000 of these on the boards. If you have a mechanical engineer in your production department that's worth half his weight, he's not going to put something like that from a Radio Shack on your board. Chances are, if he uses that cap at all, he'll use something where the leads are cut right back to the body, and it'll insert them on the board. So let's try something like that. If you'd like, bring up a second marker for me, please. And let's tune that one. So now you come in just for a cursory check to make sure things are okay. You already have 50,000 of these boards rolling down the line now. And you come to me and remember before we were at 43, come in, I said, well, your signal's failed. Well, what happens if you look at the first marker now where I had 35 before, I only have about 12 dB of rejection. My notch point for this filter has now moved to 72. And you know why, Steve, right?
Yeah.
The real problem that's happened is on this long-legged capacitor, there's more happening, especially as you move up in frequency, than meets the eye. You have the capacitor itself, the plates and the body. But as you move up in frequency, the legs on here, the leads, start acting more like plates of their own with air as a dielectric between them. So what happens is your capacitance effectively decreases because there's some parallel with it, and your frequency shifts up accordingly. So what happens is something with just a single cap where you have a very well-defined point, as you can see by the slope of that, you may miss your signal entirely. And as you go up in frequency, if your problem's, say, not at 73, if it's a 200 meg or a gig, you may miss this by hundreds of megs. To make matters even worse, chances are if they revamp the board you're using to incorporate this, they'll use a leadless type of part, a surface mount. By the way, in this type of device, a capacitor, you'll find that the axial leads are the worst because they're close. If you go to radio where the leads come out the end, then you're in better shape. As a matter of fact, that is exactly what a surface mount component is a radial where the leads are taken off completely and the ends of the bodies just form the leads of the device. And the typical what I have here is the same configuration we had before, except for it's a surface mount component device.
Now, it may be a silly question, but all of these components have the same value?
All these are identical values. At least measured and sold as identical. In reality, with the leads, they vary quite a bit. Now, as you see here, I've used a surface mount component. Now we're down at 113 megahertz, so we're at 40. Even at this low frequency, now we've missed by about 70 megahertz from where we originally tried to get to, which means that if you look at the first marker, it's almost right at 10. So we basically are not attenuating the signal we want very much, if 43 was our intended signal to get rid of. And once again, as you go up in frequency, this mismatch becomes worse and worse. So generally, you want to keep your leads short on these devices. Great. Now, there are some other things we can do to mitigate this situation a little if you must use leaded parts. One of them is to use different filter configurations. You can put these caps and inductors in multiple shapes. Some are classics. You get things like Chernobyl, which have 8 stages on it. Or you have simple things like we have here a T filter, which is basically we have 3 caps in the shape of a T. We have 2 inductors that move along and a cap to ground, which forms a T-network filter.
Oh, that really filters everything out.
Yeah, you went off.
Which one of these?
Yeah.
'Cause
Well, you had it a second ago. Okay. If you turn the filter, we want markers off. We won't need the markers. We'll just need one at this point. As you can see from the T filter, we have a much more defined slope of the curve. And if you take the one marker down to the peak of the notch, or the null of the notch, you will see here that we have approximately 80 dB of rejection. So this effectively works a lot better than a single cap. But unfortunately, it still has kind of the same parameters. It still forms a steep notch in the circuit. So you still have to be right on with your final device. But this will give you a lot more rejection. Say that 30 dB before wasn't enough. You need 40. And you could also have rejection all the way along the slope if you need more. In addition, we have another type of filter which is called a pi filter. And the reason it's called a pi is because it is shaped with capacitance in the form of the pi mathematical symbol.
touchy little fixture.
There we go. And as you notice with the pi filter, you do not have as much rejection or a bigger notch as you have with the T filter. But one of the advantages of this, if you would bring up a second marker, is you have a flat area where you have a bandwidth selection here. So on this I can go all the way from, where's marker 1 at?
Marker 1 is down here.
What frequency? Marker 1 at 38 is at 38 megahertz. Marker 2 is up around 400 megahertz, 450 megahertz. So if I only need about 20 dB of rejection, I can put this in, and if my signal strays anywhere from 30 to 400, I will get some amount of attenuation on that signal. Then I don't have to be worried much about whether the peak of my notch falls at one point or another, because I have a wider area that I can look at. One last thing we can look at is an inductor. Steve has an inductor here. This inductor is in series. As the impedance of inductor, the inductor is actually 2 pi FL, is the actual inverse of a capacitor. So these devices where you would put capacitors in parallel to ground to it, these you would put in series with your signal, and they will have the same effect as a capacitor. And if you look here, this is in series. It almost looks like our original capacitor we have, where we have a defined notch at 40, minus 40 dB. Typically for filtering circles, people at the higher, these are used only in lower frequency ranges. So what happens is you have an inductor at the higher frequencies, you end up with problems because they're wound of having straight capacitance that forms in between the inductors. So this basically what we need, just showing that you got to be wary when you use these devices. You really have to know what frequencies you want. And if you prepare early, your mechanical engineer or designer should leave on a lot of highly susceptible trace have signal lines, actually traces for you to put surface mount type devices on. And if you're careful, you can make this work in trying to get fixes. Well, now you know everything there is to know about passive components and what not to do.
Great, great. Thank you for that demonstration, James, and thank you for being on Espresso Engineering with
You're
us.
welcome.
Your information was very valuable and hopefully will help a lot of people out there. And that's it for this segment of Espresso Engineering. Tune in to Espresso Engineering next time and see what's on the plate. For now, goodbye, and tune in at espressoengineering.tv. Thank you.